Welcome to my project video for the UCL Computer Science Masters, building an advanced speech recognition engine for the NHS. First, we look at the context. The NHS currently has doctors and nurses input patient data by hand or on a laptop. This has to be entered into the hospital's patient administration system and then coded, which takes up a lot of time which could be better spent elsewhere. Strict legislation like the Data Protection Act prevents patient data leaving the European Economic Area, and this makes the use of external speech recognition engines complicated. In addition, even though accuracy is generally good with these speech engines, there is still room for improvement. For example, Google's speech APIs have an error rate of a little under 5%. The problem we tried to solve is the NHS requirement for a private speech engine which can be used to store transcribed data on NHS-owned servers. We also want to improve the accuracy for specific areas of medicine. Our chosen area was urology. To understand this project, we need to look at some definitions. Two of the crucial parts we discuss are acoustic models and language models. By an acoustic model, here we mean an engine which transcribes processed audio directly into written text. In our case, we use one based on the industry standard, Connectionist Temporal Classification. The language model is a module which assigns probability to sentences using probability distributions, and in our case uses this to make the sentence more sensible. The label error rate is the average normalized edit distance between the text produced and the text that was meant to be produced, and it's our measure of success in this project generally. Finally, the spectrogram is a numeric representation of an audio file which can be processed by a neural network as features. Our solution makes an acoustic model with a small vocabulary. We search through a large corpus of text and find the most common words. We then find the audio files which only contain these most common words and train our acoustic model on these files. The idea here was that by using a smaller vocabulary, we would be giving the neural network a smaller state space on which to train. It would therefore require less data and less time. We would then use a language model trained on simple text from urology-related PDFs to both increase the size of the vocabulary and to make the output more accurate. The hope was that we could use this to achieve the specificity through training on simple text. We will discuss the unit testing of each part after describing its function and training. Manual testing of the final product will be done last. This is the structure of the package which searches through the audio data. In the Subset Maker package, the test downloads directory contains some example audio from the total corpus. If we run the initialize module in Subset Maker, it searches through these. It produces a master file, you can see here, of JSON objects describing all audio files. A serialized object file containing the top 1000 words in top words, a path relevance file which assigns a variable of range 0 to 1 describing the relevance of the file to the vocabulary. Next, we'll remove all the less relevant files. If we change the bottommost relevance factor in the bottommost JSON object to 0.5 instead of 1, and save it, when we run the checker module, it produces another JSON file containing only the most relevant audio files to our chosen vocabulary, subset files. You can see the bottommost file that we changed the relevance to 0.5 on is no longer here. We tested the subset files to see how many times each word from a vocabulary appeared in the subset and found that 238 words appeared 0 times. As a result, we reduced the vocabulary size to the 762 words which did appear. But from testing, we see words appearing less than 10 times in the subset files, and that's what's shown here on this graph. This was flagged as a potential issue. Here's the structure of the code used to process the audio files into spectrograms. In testing for this module, we checked two libraries, Python Speech Features and Librosa. We used a simple acoustic model as an example and trained on a single sentence to check which spectrogram would be better for our purposes. As we can see, the Python Speech Features trained faster and smoother than Librosa features, so we decided to use this to process our audio into spectrograms. If we move one of our JSON files into our processor, then we can extract the audio and text and turn these into a set of spectrograms and numerical representation of the characters respectively. These are then stored in the serialized object files in data 1 and 2. We do this by running the main module in processor. Sorry, the initialize module. And you can see here the float arrays are the spectrograms, and the integer arrays are the numerical representations of characters. I've just started the acoustic model training on the set of spectrograms that we just produced. The diagram of the TensorFlow graph which builds the CTC network is shown here. It loads the features and labels, holds 10% of them back, and trains on the rest. At the end of each epoch, the test set is used to check the current accuracy, and the label error rate for this is printed alongside that for the training set. At the end of training, the remaining 5%, the validation set, is passed through, and the label error rate for this is printed. This was 0.277 for our first train. This diagram shows how the language model was trained on a set of 5 texts. Five example PDFs are stored in the test directory of the language model package. In a moment, we'll run main and show how these are processed. By running main, the texts are analysed and 200 of the most frequently used words are added to our vocabulary. This total vocabulary then has the unigram probability distribution produced from it, and this is stored in the final word frequency file as a serialized object. Here you can see the final word frequency file. Now running main, and you can see the main folder in the language model running through each of the PDFs and extracting the correct the text files, the strings from those texts. When the transcribed text enters the language model, it is broken down into a serialized, words, and each word's edit distance is checked against all the words in the vocabulary. The words with the lowest edit distance then have their unigram probabilities checked. The word with the highest probability is put in place of unrecognized words. For example, here are 3 sentences output from the acoustic model before and after passing through the language model. The tests show that small errors are fixed correctly, but for heavily garbled sentences, while they're made more sensible, the meaning is still unclear. For the final product, we integrated the two parts with a simple user interface. The modules are shown here. Most code is contained in the main CTC engine module by necessity. The user interface contains a record button and a text area. While the record button is held down, the microphone records the text. When released, it stops. Aside from the unit testing we've discussed, for manual testing of the final product, we made 3 sets of test sentences. Set 1 had been seen by the acoustic model during training. That's this set. Set 2 had not been seen during training, but were composed only of the vocabulary on which the acoustic model had been trained. Set 3 contained 1 word from the language model augmented vocabulary in addition to the others. Here that word is assessment. If we put these 3 sentences into the final product, the boy threw back his head with pride. The blood just fell out. Search the assessment room. Each of these sets contained 10 sentences, and we calculated the average edit distance from the correct transcription for 3 different scenarios. The red bar shows the average edit distance for an acoustic model trained on the entire dataset, but without the language model. The yellow shows this same acoustic model with the language model. The blue shows the acoustic model trained on the reduced dataset with the language model. These results show that reduced dataset worked better on phrases it had seen before, but considerably worse on new variations. When trained with more data, even the words were less relevant. The speech engine performed better. In addition to the testing also shows that even a simple language model can improve the accuracy of the output with respect to the transcriptions. In conclusion, having a smaller vocabulary doesn't appear to reduce the need for data. It may well be that as the acoustic model outputs characters, effectively phonetic syllables, these are not reduced by having a smaller vocabulary size. Having more training data was shown to produce a better model in spite of the reduced overall relevance of the words. The language model did make more sensible outputs and did increase the accuracy of the transcriptions. We managed to produce all the required components and functionalities, but more data and further training will increase the accuracy. Out of our requirements, we met 14 out of 14 of our must-have, 7 out of 7 of our should-have, and 3 out of 4 of our could-haves. Future work should focus on obtaining further open-source datasets to improve accuracy and modifying the code to work on GPUs to increase training speed. A next step would be to set up a server and produce functionality in the product, which would allow users to send corrected transcripts and recorded audio to the server, where the model can be retrained and updated. Finally, the system should be modified to use more complex language models, including higher-level n-grams, Kneser-Nye smoothing, and potentially RNN-based architectures. Thanks for listening, and I hope you enjoyed the video.